Welcome everybody to tea time. Good news is we're breaking the rules. We're using chairs. Don't tell the fire marshal. I like to break the rules. You're gonna be good scientists. You gotta like say, why are these rules here? I don't care about them. You have to think for yourself. That's the right thing to do.
Just like for a really good reason that those rules exist.
Let me introduce Brian Tanner. Brian Tanner, he was here. He studied as a student, and he went away to Winnipeg.
Became an accredited fire inspector.
Accredited fire inspector. That's not a joke at all. He's a fire guy. Yeah, so I have to be careful what I say about that. Okay, and that was by way of introduction from Csaba. Please no introduction, Csaba. Welcome back.
Thank you. How long do I have? 50 minutes?
20 minutes.
Okay.
And then 10 more minutes for questions.
All right. Okay. Yeah, that's good. All right. So thanks for having me. I guess. Okay. So QuickTime is taking over my screen. All right. Anyways, today I'm going to present. It's my pleasure to present to you Politex, policy iteration using expert prediction and advice. And this is joint work with Nevena Lazik, Yasinabas Yatkori, Kush Bhatia, Peter Bartlett, Gellert Weiss, and myself. And this was a collaboration between all these entities. The talk is mostly based on a work that was accepted at ICML, and that's the link to the paper. Okay, right, good. So what are we trying to accomplish here? Recent years have seen a lot of excitement about using neural networks together with reinforcement learning algorithms, and we have seen lots of successes. And if you look through the literature, most of these algorithms are model-free, right? And as such, it's kind of a little wonder that they even work. Because if you have learned anything about the theory of all these algorithms, these are very brittle, unstable. You can construct counterexamples that show that all of them can break very easily on very small problems. And so you must be wondering, like, why do they work? And so here today, I'm not going to talk about these other algorithms, but I want to just set up to solve this goal or address this goal of designing an RL algorithm which is model-free. I will be specific about what I mean about that. Well, the algorithm should be able to deliver a lot of reward. So we're interested in the undiscounted problems. We want to maximize total reward. Discount factor is an artifact. We just use it to make our lives easier, but today we're not going to discount. The environment is going to be a finite action MDP. If you're interested in the other case, when you have infinitely many actions, then you're welcome to ask questions at the end of the talk. And we assume an online access to the MDPs, that the agent who is learning about the MDP, the environment as an MDP, can interact with this MDP by sending actions to it and then receiving observations which can be used to do various things. And so what's model-free about this approach is that we assume that we have access to a black box. This is a value function approximator, which we assume is able to estimate value functions for the policy that is being used to interact with the environment. So the way it works is that you fix a policy, you start using it, you collect data, and then you assume that you have a black box, the neural network, which is able to deliver more and more precise estimates of the value function up to some accuracy limit. And we want to design this stable RL algorithm, which is guaranteed to perform well under these conditions, regardless otherwise what the MDP is. Okay? Is the goal clear? Okay. All right. Without further ado, let me introduce you to the Politex algorithm. It's going to be an algorithm which is very, very similar to all the other algorithms that you know and love from the literature with some small differences. So it's going to be based on Boltzmann exploration, and you might think that like that's an arbitrary choice. To some degree, it's an arbitrary choice, but it's not so arbitrary. I'm going to argue that Boltzmann exploration is kind of a nice fit in this case. And the way the algorithm works is best illustrated by this figure. So it's like an actor, critic, or policy iteration type algorithm. There is an actor which uses a Boltzmann exploration on some action value function. And it uses that to collect some data. So that policy is run. While that policy is being running, rewards are collected, observations are collected, actions are collected, transitions. They're all sent to this value function approximator black box. So that's the black box where you can put your favorite neural networks in. And we assume that if we feed this black box with enough data by using a fixed policy, then it will be able to deliver a good approximation to the action value function of the policy that has been used. Okay? And so the black box indeed does that. So you learn a new action value function. And then what you do, normally what you do is that once you have the action value function, you are acting greedily with respect to it, or you add a little exploration. It could be a Boltzmann exploration put on the top, or it could be epsilon greedy on the top. And what is different here is that rather than doing that, we are building a memory of past action value functions that have been estimated through this process. So the process works in these phases. It's like policy iteration. While you have a policy, you collect data, you build an action value function estimate. It's a neural network. You save its weights. Okay? And whenever it comes to acting, you have all these weights for all the past neural networks that you trained. And whenever you encounter a state, what you do is that you ask all the neural networks for reaction values for all possible actions. That's why we have to have finitely many actions here so that this computation is feasible. So you ask for the action value function for all of these neural networks, and then simply you sum them up. Okay, it could be a weighted sum, so action-wise. For each action, you have different values for corresponding to the neural networks that you saved. They all give you some values. You sum up all of those, and you do this for all the actions, and you put Boltzmann exploration on the top. For Boltzmann exploration, you need to tune the temperature or the learning rate in an appropriate fashion. And I claim that if you do everything right, this is not so hard to do. Okay, any questions about the algorithm? Yes?
So the save neural network for the last policy?
No, it's like, so if you ran this algorithm for p phases, so 1, 2, 3, and so on up to p, you save the neural network for each of the phases. So these represent a phase when a fixed policy has been executed. So for all of them, you have a neural network. So this gives you one action value function. This gives you another one. This gives you another one. And the last phase, the current phase, also gives you an action value function.
So different policies as well as different executions.
Pardon me?
Is it different executions and also different policies? Yes, different policies. Different policies.
Right. So for each of the phases, you have some policy that you're being executed. Either this should be the action value function of that policy, but maybe there are some approximation errors. Okay, so that's how it works. And then you ask for the current state and the action values, and then you sum up everything up. Okay? And then you exponentiate. Yes?
So there's no forgetting? Your memory grows?
So you can do some weighting. There are different ways of. You might think that this can become too expensive. Maybe in practice you're going to use a finite buffer. I'm going to talk about this later. Okay. So why is this good? Well, intuitively, the reason this might be good is because you're learning faster by being slower. So here, you're using all action value functions. And it seems to be counterintuitive, like maybe like you shouldn't be using all of these all at once. But because you're doing this, you can shorten the phases during which you fix a given policy. So when you have a fixed phase and you're running a policy for a while, you collect some data. And the shorter the phase, the higher the variance. So now you will be able to shorten the phase. You kind of have an averaging effect. And since the policies are close to each other, using old policies is not going to hurt you that much, I argue. Okay? All right, I spent a lot of time on this. So the main result, theoretical result, is as follows. We have a much more general result. This is more like an example of how you can use the more general result. So imagine that you have this black box, and this black box approximates action value functions up to an accuracy of epsilon plus 1 over root n after it was fed with n transitions. Okay? So there is a floor for the error, that's the epsilon. And what you want is that you want your performance to be epsilon near optimal. So the way to express that is just to say that the average regret of Politex after a certain number of steps is also proportional to epsilon. I'm hiding constants here, plus some function of time which decreases with time. It's a polynomial function of time. The exponent is not the nicest, not the best possible. We think that it can be improved, but at least you can see that it decreases to 0. So in the limit, all the error is attributable to the approximation error, which is the epsilon. Yes?
Verify steps in the environment, or steps the number of policies you follow?
Steps in the environment. I only care about steps in the environment. I don't, yeah, like because the other is the internal detail of my algorithm. I don't really care about that.
Does it matter what P is versus T?
No, I have to tune this algorithm in a careful fashion. So I'm not giving you the precise statement and precise tunings, but you can look up the paper if you're interested in details. Okay, any questions for this? Yeah.
So the loss here is like how they return it. I mean, like the regret is basically based on the return the policy gets.
Yeah, it's like the total reward collected, and from that, subtract the total reward collected from the total reward that would have been collected by the optimal policy as the regret. It's like you're just like offsetting the rewards so that you can compare different environments. Because otherwise, if I, shift every reward by 100, then like all the results would change. But this way, it's like offsetted. Yeah. Good. Yes. Yes. Yeah. Everything is hidden here in this assumption. So what you're looking for is there. I don't need any other assumptions for this high-level theorem. But you are rightly asking the question, can these assumptions be ever met? Okay, can I build a black box ever with these properties? It doesn't have to be finite state MVP. So the result was, okay, I proved the result for countable state MDPs to be precise, and there is some technicalities for extending to continuous state MDPs, but I think that it would extend. These are really technicalities. I'm happy to talk later. It's not that trivial to extend actually, but okay. Anyways, so how to build a black box? So the theoretical results would be empty if you wouldn't be able to demonstrate that you can ever satisfy the conditions. So okay, can we do it with linear function approximation? Because maybe the neural networks can do it, but like maybe yes, maybe no, who knows? So can we do it with linear function approximation? And we took the LSP algorithm because it seemed easier to analyze than the other algorithms and convert it to a batch algorithm. So we are solving the projected Bellman equation, the empirical version of that with this LSP style algorithm. And so here we're going to need two more, like the assumption that we want to meet is going to be met. If we make some assumptions about the features, which is an innocent assumption, you can always guarantee that this holds. It's more like technicality. And this is a not innocent assumption. It says that for any policy pi that you ever encounter or can ever fed to the system, this black box or this estimator, you want the minimum eigenvalue of a certain matrix to be positive. It means that all features are excited. So you kind of like need to be able. So what is the catch? This is going to be satisfied. So the hard part is to satisfy this with respect to the actions. So these are features of state action pairs. I'm hiding these details. But the Boltzmann policy might not want to choose some of the actions too frequently. And in those cases, how are you going to learn about those, right? So there was no explicit exploration beyond Boltzmann. And you might be worried about this. Well, so we have this assumption, and you can meet this assumption, then you're good. You can imagine cases when you're designing features such that these assumptions are met. For finite MDPs, if you use tabular case, then this assumption is trivially not met. So later on, I'm going to talk about how to relax this. Okay.
I just want to mention that paper by you, Bert Sekas.
Yes.
That you is Janie.
Oh, no one knows that? Everyone knows that.
Call her Janie.
Right. We stole some results from your paper. Not stole because we cited, but it was really useful. Thank you. Yes. Okay. So far so good. But like, why this algorithm? Why insisting on Boltzmann expression and so on? So first, so here is the gist of it. So imagine that you have your current policy pi. If you write the regret, that is the performance relative to some base policy pi 0, which could be the optimal policy for that MDP, then after some mathematical manipulations, you arrive at an expression like this. And this is a very compact way of writing things. So here this is a very ugly notation. So that to make the equation fit this box. So this hides a sum over the actions, a weighted sum, where the weighting is given by the policies. So these are stochastic policies, okay? And you take the probability of taken by this policy of any action. You multiply the corresponding Q value. You sum over all the actions. So it's a linear weighted sum, okay? But this is with respect to the current state, right? Okay, so that's the notation here. And so that's a linear expression. So what's important to notice here is that you want to keep the regret small, then you have to worry about keeping this term small, okay? And you might think that, oh, this is really hard because, oh, this is the stationary distribution underlying the baseline policy that you're comparing with. Because like we have so many states, but okay, like let's forget about the station distribution. For a given state, if we can keep the regret small, just this expression, we keep it small, then we should be fine because then the weighted average will also be small. So keeping the regret small is made difficult because by the time you're running policy pi, You don't know Q pi. That depends on the MDP. That's complex. It's a complex dependence. Yes.
Okay, and I'm going to slow you down just a little bit. So Q, do you want it to be large or small?
These are rewards. These are rewards. So this is like the best possible Q value that you can imagine. You want max, large. But you want to minimize this because this is your policy. It's flipped. It's a negative sign. This is a regret, right? Compared to a good guy, like the good guy could take the max here.
So that's how much worse you're doing than the best policy.
Yeah.
Not that different.
Right.
And weighted by the chance of seeing that states.
That's right.
See the states which have high differences very rarely.
Right. Okay. All right. So you're maximizing, but you're minimizing this expression. Okay. And so that's complicated because this Q pi is unknown at the time you're selecting pi. So that seems to be like a circular reasoning. So how do we break out of this? Well, I made this line dotted, meaning that I'm just going to assume that this is chosen, this Q pi function is chosen by an adversary. It's chosen in an arbitrary, history-dependent way. Okay, and the adversary can do that for me. And I'm asking the question, is there any algorithm that can keep the regret for every state small? And the answer to that is that you just use Boltzmann explanation with respect to the sum of the previous Q functions that you have. And now the next thing is that these are the three Q functions. You can replace them with estimates. You have to bring in the estimation error. But they're just like technicality and just part of the analysis. So this is why Boltzmann explanation comes into the picture. And this is why the algorithm takes this particular form, because if you want to minimize regret in this linear setting, so the linearity comes from these weighted sums over the pi here, then the algorithm to be used is what we know as Boltzmann explanation. In the online learning literature, it is known in various names: exponential weighting, mirror descent, and this is not the only algorithm, but this is kind of the standard algorithm that people would immediately suggest if you ask them what to do in online linear optimization to minimize the regret. Yes.
I have a very stupid question. How do you know what the optimal policy is?
You don't need to know. In order to minimize this, you're minimizing this with respect to regardless of the choice of pi 0.
Oh, you are?
Yeah, you are. Even a worse choice of pi 0, you can minimize this. I really ran out of time, but nevertheless.
Yeah, so
Many questions, so we are kind of mixing the question time into the talk, yes.
sorry, last one for me. First and last one. So even if you have two action values, so these Q pi, are they true action values or are they estimates?
For the algorithm, you replace them with estimates.
Okay, so
And that's going to be fine because then there are some error terms that arise, but you're controlling them by making the assumption about the black box.
okay, so the question is, if you have two action value functions, and these two action value functions can be very close, but the other, like the policy are totally different, then how do you decide? So in this case, the regret will be very small, but the policy pi 0 and pi are very different.
You don't care about how different the policies are if their underlying Q functions are the same.
They are similar, but not the same.
Yeah, the policies are similar. There is smoothness going on in MDPs. If you have similar policies, then the action value functions and the rewards are similar, right? You can't have, okay. Some MDPs you can have this, but under the assumption that if you're running your policy and you can estimate the action value function well, then there is no problem with this. Yeah. Okay. All right. I have to make some executive decision. I think we talked about this. You can forget the past. You use a weighted sum and so on and so forth. the important thing is that there is a constant factor memory overhead if you use the circle buffer, and that prediction time is also a constant factor overhead, and training time there is no overhead. Experimental results very quickly, comparing with DQ1. These are rather preliminary on Miss Pac-Man. And what I like about these curves is that they all go up, of course, and they don't come down. So like the crazy thing about DQ1 is that, well, if you wait long enough, then it goes up. But sometimes it completely collapses, and then it goes up again. And like I just freak out if I see that.
Your curve goes down on your wheels. Not for
Yeah, I mean, like because like there are random events here, so of course, but it's not like it's collapsing. And when this collapse happens, then really that algorithm, if you look at it, it completely forgot what it knew, and it's not good. All right. Anyways, we have more results, and the algorithm we compared it to RSPI, which is not trying to do anything too clever, and a randomized version of that by Ian Osborne and Ben and Roy, and we are on par. So here's lower is better. So we are red, and the black is the best competitor, and the blue is just LSPI, which everyone knows. Okay. So it seems to work.
how much tuning of all those hidden parameters?
So we didn't do much tuning. It's I don't think that we like the theory suggests some parameters. We just like take them and like run the experiments. And for the Atari experiments, we just took, like there are lots of experimental details. We took some existing software package, and we just replaced the way the policy selection works, and made this high-level choices about how lengthy the phases are going to be, and then that was it. And sensitivity was pretty good too. Okay, so relaxing assumptions. So you might worry about this. This assumption that you expect to learn about actions which you didn't try. So how is that possible? Many times it's not possible. So here I want to introduce another black box, and this black box goes to places. Its job is to try different actions and go to different places. So I assume that someone gives me an exploring policy, which is like this curiosity-driven policy that goes everywhere. Its job is not to collect a reward. And if someone designs such a policy, I want to design an algorithm that can make use of that policy in the setting where I care about maximizing reward. So you can expect what I'm going to do. I'm going to switch back and forth between the exploration policy and the Politex suggested policy inside the loop. And this algorithm, I claim, is an okay algorithm. Its regret is still sublinear. You can tune the phases in an appropriate fashion. If you run this algorithm, I said it's an okay algorithm, and it performs worse on Miss Pac-Man. Well, this is the price that we switched in this exploration policy. This exploration policy here that goes everywhere was learned based on some artificial reward function, and it's assumed to be given. It's not learned together. Okay, so it's learned ahead of time. It's just like this policy that explores everything, and it bumps into the ghost, right? And so the performance can, like, you expect it to drop, right? But at the same time, it's okay, like, still learning. Some other environment, I really don't have time, but in this case, lower values are better. And we are the purple, the orange, and the red, different versions, and we are always very good. And other algorithms are not that good. And this is a scaling problem. So this is a problem where you can scale the size of the problem, and the problem becomes much, much harder for simple algorithms, and our algorithm is able to keep up with it. It's not really a surprise. It was designed to be able to do this. This is a swing up problem. Here you can see that Politex, Boltzmann explanation, has no chance. Even with this clever let's sum up previous action value functions, there's a classic swing up problem, you have an inverted pendulum, you want to swing it up. And if you add Boltzmann exploration, it will never ever see a reward. You get a reward when it swung up. Okay, all right. So I claim that this is the first algorithm that is guaranteed to work in the non-realizable value function approximation setting. We got some theoretical guarantees and also seems to work in practice. We have lots of ideas and tried some of these ideas. So for example, the algorithm is using adaptive learning rate tuning that we got from the online learning literature, and it is actually very helpful to make it stable and reduce the number of hyperparameters in the algorithm. And it seems that this idea might give you an answer if you ever wondered about why everyone is suggesting this KR regularization together with policy iteration algorithms. Here it appears in a very natural fashion, right? You get the regret bounds because you're doing this. Okay, and lots of plans for future work. Okay, thank you.
Well, we've used lots of question times, but let's have one or two more questions. Abhishek.
So you said that you can use any reference policy, and if you minimize the regret with respect to that, this will work. Can you give more intuition as to why that is the case? Why if you're using a policy other than the optimal policy to minimize the regret?
Oh, the optimal policy would be the toughest competitor to compete against. The reason I'm talking about other reference policies is because I had a lot of conversations with Rich that the optimal policy might be just too tough to compete with, right? Like it might go to places where you'd never be able to go. And then you can choose your other policy that you can compete with, and you can modify the conditions that I have for the future expectation that, like this excitation condition, for example, will be easier to meet, right? If your policy tends to go here, then you can compete with policies that tend to go the same place.
So this can only learn policies as good as those exploratory?
No, it depends on, right? So the Achilles heel of this problem is, of course, the exploration problem. That you want to get to all the places, and for that you have to do something clever, which this algorithm is not doing. The second algorithm, which is the exploration enhanced version, is mixing in this exploration policy which is designed to go to places. And if that black box, the second black box, is a well-chosen one, then you can compete with the optimal policy as well. But I would warn you not to try to compete with the optimal policy. That might be too tough. You just want to be reasonable, right? Yes?
Csaba, in that, the second Miss Pac-Man slide, you were showing your two algorithms, and you were saying that the exploration policy was bumping into ghosts a lot, and that hurts it in that graph.
Yeah.
Is it a sensible thing that, I know you're trying to maximize total reward over the lifetime of the agent, but could you just sort of take the max Q values without the exploration and then compare that? Like, would that be a much better policy?
I think that these are two different things that you're talking about. The max of Q values, you would switch from Boltzmann to just greedy, or?
So my understanding is when you had the two Miss Pac-Man results, you were saying that the random exploration that you were doing with the second algorithm was what was costing you on that graph?
Right. Because like the phases are split in between just using the exploration policy for a while to collect data. And then after a while, for the longer phase, I'm using the policy that I want to avoid. And then I have to switch back and forth to just guarantee that I'm in the limit going to visit all the state action pairs. And of course, over time, the ratio of how much you're using the exploration policy decreases, but like for the settings that come out of the theory, if you implement the algorithm, this is what you see. I mean, you can tune everything, but I really don't like when people do that and then report results for the best possible setting that they could get. Also, I think for Miss Pac-Man, what's important is that exploration is maybe not that important. By the time you learn a good representation with your neural networks, you have seen so many things. I think that's the other reason that there you don't see much success with this approach.
So I guess what I was trying to get at was, at that point, after you've learned for a long time, could you turn exploration off all the way?
The algorithm is doing it, but it was not running for long enough time. It would reduce the exploration.
One last question.
So in DQN's case, if we use multiple networks and store them at regular intervals, and then when we're selecting an action, we average over previously stored value functions, would you expect that we won't have this collapsing effect that we're getting?
That's Politex, right? Just we add Boltzmann exploration. Are you asking whether if this epsilon grid is going to work as well?
Yeah.
Yes, it will. I think it would. I think we actually ran some experiments. Okay, so back to like, is it really Boltzmann exploration that's doing something clever? Well, even from online linear optimization, we know that if the adversary is not that adversarial, then you can just follow the leader. Like that's like being greedy, or epsilon greedy in this case, because you need to add some exploration. So I expect epsilon greedy to also work well.
Okay, thank you very much.